Says we're streaming. Hi, I'm Bob Doyle, the information philosopher, webcasting to you from my ITV studio in Cambridge, Massachusetts. It's Friday, and so it's Einstein Day at the Information Philosopher. And I want to give you a report on how I am progressing with my book on Einstein called My God, He Plays Dice, in which I argue that Einstein reverses his position and now accepts the idea that there is ontological chance in the universe. My work on Einstein, I must admit, has slowed a bit as a result of doing these lectures online 5 days a week. I thought it wouldn't be much of a problem. I would still be able to write clearly all weekends, but it turns out that the technical problems I've had in my ITV studio have slowed me down, and I'm still around chapter 17 or 18 in this book. So I'm hoping to get along with it and be able to add more. You'll see the book is just a draft at the present time, many blank pages, incomplete material. And I want to turn to it much more fully in the coming weeks. So the particular thing I want to complete at this moment, in addition to telling you about my studio, is this idea that quantum probabilities are actually not so much a property of the particle. Sometimes it's thought of that the wave is a way of describing the particle and the wave moves along imitating a particle. We're not going to go there. Instead, we're going to give you quite a different picture of probability as a property of space, much like the property of space Einstein saw as a result of material distribution around space. Actually, the matter gravitationally distorting the space, creating it as a curve, which makes the particles move along what are called geodesics and appear to be straight lines, but in a curved space, they are not straight. So let's just for a moment go to some points I need to make about where I am today. I'm basically making very slow progress here on my book. Let's see if I refresh this page. I might get it to turn bold for us. There we go. So it's a little more readable on your screen. So as I point out, I've had a few technical problems in my ITV studio. I just want to mention them to you because some of you may be interested in someday having your own studio. For 20 or more years, I've been proselytizing the idea that young people who would like to start up a television program need not go through their cablecaster or their or broadcasters. They could instead create their own work environment where they have modest cameras. I've built studios for students in some schools, which today can be built with a few $100 camera or cameras. Ideally, you need 2 or 3 cameras. I have quite a few here. I'll show you my view from my #1 camera up here, where you can also see the kind of tools I've developed to be able to switch between my blog here and my website here on Albert Einstein today. My switcher up here, which changes between the different cameras. I'll switch to camera 2, which is an angle off to my left. By the way, you can see in that shot that I've added an earphone. I must apologize to those of you who had your eardrums damaged a bit by my very loud sound when I played a YouTube video. I wasn't able to monitor this. I've had to build a system which takes in the sounds and mixes them together and then puts them in my ear, much like network broadcasters, regular cable casters and so forth. I now have that in place, and I hope I'll be able to manage my audio for you better in the future. This is my main view screen. This is the screen that's off to my right, your left perhaps. You see a picture here of my multi-screen system, multi-view system that allows me to see what all the cameras are doing. This is a camera off to my right, again with a view of my studio. I think it's working pretty well. I'm now down to about 25 minutes of setup time to make sure that everything is working. I'm pretty much ready to go in 25 minutes. Number 6 camera here I'll touch is the overhead camera, so I can see down on my books and everything, and I can show you how this can be pulled back so as to reveal my full working environment. My switcher on this left is my blog post that I read from, and over here is Albert Einstein. Up here is the poster that I use to have the beginning of the show and the end of the show and so forth. Finally, my most distant camera is off to my right here, where you can look across and see my schedule on the big screen behind me. I can put up on that screen my poster, which I use to start the program, and then I'll use it to end the program when I'm done, trying to get a little bit more organized and having a reasonable presentation of each of my lectures. So let's go back to what I'm talking about from here. I actually had a failure of my streaming equipment, and let's see, I need to put this here and this here. I had a failure of my box that I used to stream my video and send it off to a cloud service that in turn relays it to YouTube and Facebook and other places in the future, should I want to do that. It's a wonderful service from Teradek. They call them core services or cloud services, and the tools that I use are called their cubes. And I have a cube here which encodes my program, and another cube at CCTV where they are now playing my program live. Perhaps I could show you that if I go to camera 1, for example, and if I use camera 1, which I've practically never done, manually to zoom in, I have to zoom up a little bit, and you see the rest of my lab. And let's just zoom in across the way and see if what you see on that screen there's my Macintosh development poster. You see I'm zooming that distant camera, and on that camera is my head, because I'm basically giving you a view which takes a few seconds, 1, 2, 3, 4, before that shows up on the screen. There it is, 5, 6, 7 seconds. Okay, we'll bring that back to my preferred view here. Let's go to camera 3. I'm back here. Reset that other one later. This has been a challenge for me, quite apart from the challenge of getting all my ideas together and taking them from parts of the website and preparing lectures on Mondays on great problems, Tuesdays on free will, Wednesdays on great philosophers and scientists, metaphysics on Thursday, and today, every Friday, we talk about Einstein. So another thing that slowed me down, kept me from writing my books, is that I now have to learn how to arrange my videos on YouTube and on Facebook into what are called playlists. And I have to take each video when it's recorded there and add this poster page, like this. Today, when my lecture's over, I'll spend another 15 or 20 minutes going to YouTube, going to Facebook, and replacing the default picture that they put up to represent each video with something like this, so you get a good visual introduction to what I'm doing on each one. And if I go here, I can show you, I've made a list of all of my lectures. It looks like this. There are a few posters missing here because the updating, my browser doesn't update them all the time. Here's a lecture today, quantum probabilities, and so forth. So that's a little picture of where I've been going. Let me go back over here to this screen and come back to my blog right here. And I think that would be, then it says, I say that I'm trying to now put my lectures up on Apple Podcasts. I was privileged to be at Harvard when the faculty got their first blogs, and they were audio blogs in those days. And at the time, Dave Weiner, the great developer of blog software and other important software for Microsoft, gave blogs to the faculty. And there's an important story that I was happy to be part of, where Christopher Lydon had come to Harvard from WBUR, where he was a broadcaster for National Public Radio, and he had a very powerful show called The Connection. Instead, he came to Harvard after BUR denied him the rights to his future shows, and he asked Dave Weiner what he could do to get his career back. Weiner said, write a blog. Christopher said, no, my gift today is my voice. I want to be having my voice on my blog. Can I add audio to my blog? And Dave sent Chris over to me, and I set him up with an MP3 recording studio in the back of my lab here. It became the Lydon Studio. If you Google Chris Lydon, L-Y-D-O-N Studio, you'll see the story of what we did together. He produced 55 shows here, and then we put them on a CD. They were audio shows. He circulated it to American Public Radio, National Public Radio, Minnesota Public Radio, several others. And today he's got his show back, and it's on WBUR in Boston at radioopensource.org. And he is a podcast on Apple Podcasts. I do not yet know how to do that exactly, and I'm in the process of taking my information philosopher lectures, these lectures, which I produce 5 days a week as videos, and I want them to be available to the massive audience for Apple Podcasts. Okay, I now say here that the good news is that improving my arguments for you viewers on difficult subjects that I'm trying to discuss has really made my work stronger, I believe. It is stronger, and the problem with that is that my animations of quantum mysteries like entanglement that we spoke about a week ago on Einstein Day, the Two-Slit Experiment, which we've done a couple times, and the wave function collapse, all of them, they're linked here. Should you want to go to those links, here, the Two-Slit Experiment and wave function collapse, you need to study them, and it's better to study them as animations on my website rather than watch me talking about them here. Although today I added a new animation about the Two-Slit Experiment, and it'll be the major thing I present for you. And I will show it to you and show you how I can play it for you, but then you can go to the Einstein page and find the animation and read the support around it again, and at your own time try to see whether you are really following what I'm describing as the possible explanation that Einstein's objective reality attitude has given us as a possible way to make more sense of what otherwise seemed to be quite mysterious. So I point out that it'll help the arguments in my book. Much of what I'm doing here is experimental. I'm trying to frame arguments myself in a way that I can explain them in a most introductory way, bring people in to understanding them. And as I do that, I'm sure the arguments will be better in my book. But the book is pretty much limited to print, no animations, no sounds, and so it's limited in its ability to do what I try to do. So I recommend you go to my webpage on Einstein, and there's a link to it at the bottom of this blog post. I also encourage you to go to my blog posts at i-phi.org, where each morning I prepare a little description of what I'm going to do during the day, and in this case I'm putting up our old animations and my new animation for today. So to the main point of what we're trying to understand today, on the left I have a picture of the two-slit experiment, which is on the Einstein page, and you may have seen it before in my earlier lectures, in which there is just one slit open. And the patterns of interference of waves coming in that one slit has a characteristic look. It's rather broadly, you see that there are light bands going off to my right there, up, and there's a band up in the center, and there's another one off to this side. However, when a second slit is opened here, we get a much more complicated and dense set of waves. They interfere in somewhat different ways. The central maximum has shrunk down to this little narrow one, and now there are multiple interference fringes. Now there are always multiple interference fringes, but they're very much smaller in the case of one slit, and they're spread out more. But over here we see that there are 5 rather visible ones and a couple showing spread out. Sometimes the two-slit experiment is described in YouTubes and especially in books as when you have one slit there is no interference, they say, and when you have two slits you get the appearance of interference. That's unfortunately a technical detail that's often misrepresented because there's always interference. We get interference from the two sides of the one slit because the waves coming off this side of the slit, even however narrow it is are at a different distance of travel when they go across at some angle, and there is some interference just because of the finite width of the slit. While we're looking at this diagram, which I've drawn up with my crude Photoshop techniques of drawing, I want to point out that the critical visibility, the visibility of the interference is really only there when the wavelength of the light coming in is about the same size as the size of the slit. If I was to widen this slit, you would see those interference patterns broaden out and disappear. Actually, if I narrow it down, it becomes just a little spherical wave. If this was a point, then it would be always equidistant up here, and there wouldn't be any interference. The interference comes from the fact that one side of the slit, light starting off there, is a little behind the light that's going off from the other left side of the slit. Okay, so this is our picture, and despite many attempts to think about what's going on here, it's always been most clear to me that Einstein always saw this more clearly than almost anyone else. But unfortunately, he didn't give us very many diagrams himself. He did write articles, and he did do at least one famous diagram that he put up on the board at the Solvay conference in 1927. And that diagram I have on my Einstein page, so let's switch over there for a moment. And here's Einstein's page, and this of course is a lot more complete than what we're going to talk about today, which is just homing in on the one aspect of the two-slit experiment. So let's scroll down and work my way through the early history, a survey of Einstein, and then particular big pieces of work like his 1905 paper on the light quantum hypothesis and the photoelectric effect, which demonstrated what he was, why he understood this as a quantum of light rather than a wave. Then in 1909, Einstein wrote on wave-particle duality, and what he wrote there is as good as anything that's been written since, and a good deal more clear. And he argues that there are two aspects to light, and he diagrammed that in words, which I've turned into an illustration, okay? What he said was that when an electron comes in, a high-energy electron strikes a metal plate. Then in the photoelectric effect, actually the photoelectric effect we're going to see up at this point when photons eject electrons. But in this 1909 paper, he said, let's imagine an electron is coming in of a certain energy, and we can control the energy, or they're being generated by an X-ray generator. And when the electron slams into this plate, it ejects a photon. Now, as he described it, eventually in 1927, he drew a picture something like this, where it looks as if the waves are going off in all directions, right? They're coming up, it's a little hard to describe this, they're going out in all directions, and yet, if that one photon at a time is created, so we fire one electron at a time, and the waves go out of the light, if it hits this plate over here, it arguably and experimentally could be seen to eject another electron, and this electron will be shown, could be shown to have almost all the energy that the original electron had, okay? The powerful electron comes in here, powerful photon, an X-ray, it hits the metal plate and it generates an electron that almost has the same energy. So Einstein is telling us, how does it work that the energy goes out in all directions here, right? And yet it gets itself all collected together again to eject a second electron at that second plate, P2 there in the diagram. Let me expand that to full screen for you. Therein lies the mystery. At a stage in Einstein's thinking, he says, somehow we've got to come up with a fusion of wave theory and particle theory together, and it wasn't immediately obvious how to do that. But what Einstein did say is that clearly, at least he thought at that time, what the wave represented was the probability of finding a particle at any particular place in the space. So if we come back to our picture of the, and let's see, I've got to come back to this one, and this one here. If what we're seeing, see, I want to bring this up, and I want this one on our screen, good. If we think of the resulting positions where particles land here in the two-slit experiment, or where they land in the one-slit experiment, there's some chance that they could land anywhere. Some parts are more probable than others, and that's why we have the big peak. And what Einstein is telling us is these waves simply establish the chance, the probability, where we should see photons landing, if they're photons or electrons landing. And when we make measurements, we should see them there. So that the waves are nothing but probabilities. In particular, and this is kind of radical what I'm about to say, it's not that the electron itself or the particle of light itself is establishing where it will go, as if it has a path, an equation of motion, we call it, a path that tells you where it's going to land. Instead, it's very simply the probability amplitude waves determine the probabilities. So my question for today is, what determines the probability waves? Those who thought, well, it must just be something intrinsic coming along with the particle. They have not really described well what quantum theory tells us about those probabilities. In fact, it's well known to a quantum physicist that the way you calculate the probabilities is to solve Erwin Schrödinger's wave equation. And the wave equation is a very simple mathematical function which we can quantify numbers for finding the probabilities depending on the shape of the surrounding material. Depending on, in the case of the one slit here or the two slit here, it depends on exactly what the volume is, where the wall, the screen on the back is, where the slit and the initial wall where it comes through is, and so forth. And what I'm saying is, it depends only on that and the wavelength of the light that's involved. We solved the Schrödinger equation for a certain wavelength. and certain boundary conditions, they're called, that surround the environment you're in. And if you think about that for a moment with me, you see that the solution to the waves, where they will be large values and where they will be small, actually they're positives and negatives, that will be different when two slits are open. So what I'm about to show you, hope to convince you, is that if a particle comes in, it doesn't matter whether it comes in this slit or that, because what it is determined by, where we find it, is determined by this distribution of probabilities inside the experiment. And those are the same whether the slit, whether the particle, a particle, if we do it so there's one particle in the experiment at a time, it doesn't depend on whether the particle comes in this slit or that slit. It simply depends on these waves. So my goal is to see if I can create an animation with that in it. Let's go back to Einstein's page again for a moment, and we go on from 1909. And here's a paper on the emission and absorption of photons from atoms, which is extremely important. And in that study, Einstein showed that the radiation that goes off in a random direction. And he discovered ontological chance at the quantum level in 1916. And I argue that that's a source of irreversible behavior. Here's the 1927 Solvay conference. And here's the diagram that Niels Bohr reports to us was drawn on the board by Einstein. I think I actually have a picture here, maybe I don't, of a more crude picture. Oh, here's Bohr's recollection of it. Right. If I start here, this is a picture that Niels Bohr added to the memorial volume, Paul Schilp's memorial volume for Albert Einstein. Here the sentence is the words of Bohr. To illustrate his attitude, I'll bring it up to the full screen, to illustrate his attitude, Einstein referred at one of the sessions to a simple example, illustrated by figure 1 of a particle, an electron or photon, says Bohr, penetrating through a hole or a narrow slit in a diaphragm, and then he talks about, you see the wave expanding spherically, and you see it landing possibly at a point A, and then in parens a point B. And then on account of the diffraction of the wave, what happens? And he explains that if the experiment records the electron at one point A of the plate, then it is out of the question of ever observing an effect on this electron at another point B, although the laws of ordinary wave propagation offer no room for a correlation between two such events. And this is from Bohr's discussion with Einstein. I just want to go back a little in this section to where I have a drawing after some other people who reported what that picture was that Einstein did, and here we have it coming through, electrons coming through here at 0 and landing at P. And after this drawing, I hope you'll enjoy the Einstein page, you'll see what Einstein actually said here. I won't read it for you today, but he explains what he was thinking, why he was concerned, and when he finished his talk, Bohr, it's reported in the original papers from 1927 that Bohr said this: I feel myself in a very difficult position because I don't understand what precisely is the point which Einstein wants to make. No doubt it is my fault. So let me take us here for a moment. And it seems to me this is an astonishing moment. And to me, it's become typical in all my reading of the papers of the time, and both the published ones and the ones which are recorded remarks said at the time, that Bohr really didn't understand what Einstein was concerned about. And that probably describes much of Einstein's work through 20 years before this paper here. This is 1927, and Einstein has been arguing since 1905 that light has a particle behavior in some respects and a wave behavior in some other respects. And Bohr has been denying that light is particles until just perhaps a couple years earlier than this paper, and maybe even at this time. I'm trying to find reports of Einstein meeting with young Heisenberg, Bohr's student, who came up with quantum mechanics. And it's clear that in just a year earlier than this meeting in Solvay, Heisenberg was not yet willing to accept the notion of light particles. Just a footnote in my research, I have all of the wonderful volumes of Einstein's writings, the collected papers of Einstein, but sadly, they've only been published through 1924 and up to volume 14. And I'm happy to say I've just been able to pre-order a copy of volume 15, which will take us through 1926, perhaps into 1927, but probably not up to the this very important meeting between all the quantum mechanics people in the fall of 1927. So it may be a few years before I have everything that I can read in order to fully understand what Einstein was up to. But I'll do my best, and I hope to have my book out by this spring. Maybe I'll be finishing up the bibliography and the other things that are needed to produce a published book, including all the footnotes and so forth, around the time that the latest writings will be published. So what we need to do is move on here. And that's the diagram that Niels Bohr said he drew. Let me shrink it up a little bit. And I argue that Einstein does accept quantum mechanics there. Eventually we'll come to his Einstein-Podolsky-Rosen paper and entanglement, and we've worked on that already. I'll come back to it again. Here's an animation, which I think may be working. I just have to press a button to make it happen, like this. I hope you'll enjoy my animations and criticize them if you think you don't understand what's going on, so I can make them better. And then I think I've got something here on the two-slit experiment. I'm hoping, here it is. Here's the one that we are working with today over on my other page. And what I've done here is to add a new way of thinking about it. And let's just read. Perhaps from my blog page, it'll be a little easier to read. Let me go over here, scroll up. The fonts are a little larger. And here I describe experiments with one slit and two slits open, showing the possibilities field, which is calculated from the square, absolute square of the wave function. And the possibilities field for two slits open applies whichever slit the particle enters. That's what I'm trying to home in on today, that what happens when two slits are open doesn't depend on a particle being in there. As long as we are calculating for the wavelength of the particle, we develop the probabilities, and those will be the probabilities whether we allow thousands or millions of photons to come in all at the same time, or if we send one at a time. And that gives us the dilemma that's usually associated with the two-slit experiment. Remember, Richard Feynman gave us this argument, this view that the one mystery of quantum mechanics lies in the two-slit experiment, and that all other mysteries can be traced back to this one. So what I'm doing with you today, and I will be doing on the website, in the Einstein page, and I'll be doing that in the book, I'm trying to say, where exactly is the mystery? And to make us get closer to that mystery, I point out that the possibilities field is a property of the boundary conditions for that space. So let's just bring that up as clearly as I can say it. The probabilities are basically dependent only on the boundary conditions for the space. Okay? So here we go with a piece of work I've just done this morning. I've taken that same diagram and I say, following Einstein's objective reality view that particles have paths even if the paths cannot be measured. I can now animate that above cases, the two above cases of a two-slit open or one-slit open, and basically show you that I'm going to let paths come in the one-slit case, and I'm going to let paths come in, electrons or light particles come in, and they will jump around, distributing themselves, these paths, according to the probabilities. Okay? All right, so here we go. I'll just pull it full screen and talk over it. Here is two slits open, and the paths are one slit open. They always come through the one slit. They come through and they randomly land according to the probabilities on the back wall. Now, when the two slits, we see that they can come in either slit and similarly distribute themselves. So that was a piece of work this morning. I took the diagrams, let's see, I'm on the wrong screen here. Let's go to this one, so it's on the back wall for me. Let's enlarge it to fill the screen. And let me talk about it some more. With one slit, they randomly appear. Notice they tend to go into the places where the probability is high, although occasionally you'll see one jumping out to the edges, here like that one. And now with two slits, you see them landing. They don't land on the spots in between the interference fringes. So right here, I've only got a few cases, but over here you see they land everywhere in that middle zone. But here there are now places where they no longer land. As soon as the second slit is open, interference prevents light from landing where it did land when the one slit was open. And that gives us that deep question, how can it be that with one slit open like this, we get light there, and when we add the second slit, we add light, but it does not add, it actually takes away light at a spot on the back wall. That's one of the to be explained properties of this two-slit experiment. And we're going to explain it by the simple fact that the waves, the probability waves, have established the values independent of whether there's a particle in the experiment at this moment or not. And let's see what I want to say here. Let's leave that on the background and try to focus in on where I do believe there still is a mysterious behavior which is just not explainable, so to speak. It remains a mystery. Because the standard way of thinking about what would be a solution to this mystery just doesn't work for us. So let me try to prepare you for that. When the particle comes in as I've drawn it here, I draw a straight line from the slit entrance. Below that point, I just have plane waves. You see, below here, there could be particles coming anywhere here, and some hit the walls. Some come up and just bang into the wall, let's say here. But when they come and land on a slit, then they travel through. Now I draw them as a straight line. And you could say, how can I be drawing it a straight line if we do not know the path that it takes? And here I want to say, let's back off with Einstein, talk about objective reality. Einstein is saying, we cannot measure that path. To measure it would mean to destroy the effects, because a measurement interferes with the particle, and that's not possible. So we can say with Einstein, not knowing its path does not tell us that there is no path. Here, notice the difference between an epistemological statement about quantum mechanics and an ontological statement about quantum mechanics. Einstein definitely thinks that ontological statements about the deep reality are possible even though we can do no experiments to establish them. We have to take it on the basis of that properties of a particle are conserved. They're not willy-nilly jumping from one place to another and having no appearance anywhere in between the two places. It's common sense, you could say. It's what he thought people accused him of, quote, naive realism, and it is in a sense naive to say, since we don't know any better, and we know that it starts at a slit opening and ends at the screen, let's just assume that it travels in a straight line between those 2 points, okay? Copenhagen physicists don't like this. They don't want to say this because they say, since we do not know or know how to measure, we argue, and they do, that there is no path, that there's no path, nor is there position until the experiment is made, and we actually collect a single particle and a detector fires or a photographic plate gets darkened and so forth. So I back up with Einstein and say, we are going to assume it's a straight line because a straight line allows it to conserve its energy. If it goes in constant velocity, constant direction, which explains a straight line, then we have the simple statement that it didn't arbitrarily change its energy. For example, what would accelerate it? There are no forces here acting on it. It's moving freely through space. Why isn't it a straight line? To bend it, you would need a force on it. And we design our experiment with no internal forces. So the straight line seems like the easiest, simple way to talk about what happens. However, let's back up a moment. The particles are coming in one at a time. How can we, what can we say about any forces that are causing it to be distributed according to the probabilities above? Why are they landing in this pattern, okay? Any physicist from the Newtonian classical point of view would say, surely there must be an explanation of why it gets from here to there. Maybe they would say something like, it must have bumped into a different part of the slit, and that caused it to either bump off this way or bump off that way, or all these random ways I'm animating here. But we don't know that. We can't rule it out, so it could be that it's something to do with interacting with the slit as it passes in. But it seems odd that this distribution of waves, which are the probability waves, can be calculated by Schrodinger's wave equation and work perfectly. So it does seem, and this is where I am in my own thinking at this time, that it is simply the waves and the square of the waves which tell us what's going to happen. That the prediction is that the particles will be distributed according to that laws of the square of the wave function. But now we don't have anything except to say, we know what the probabilities are, but we don't know what's actually in charge of where the particles go. And that, in a nutshell, is the knowledge that's missing that seems to add a mystery to the behavior of quantum mechanics. And I must point out it is only knowledge that we have statistically or probabilistically. And so quantum mechanics, according to Einstein, he said to his colleagues, it looks as if quantum mechanics is a statistical theory, that all I can tell you, all we can know from the Schrödinger equation is the probabilities of where particles are going to be found. I think in that simple statement, Einstein said all you can say about what's going on in quantum mechanics. And when he says it, he says, compared to classical mechanics, where you would have laws that told you specifically one particle at a time, you would know the exact path, the exact momentum, the exact final position. He said, in that sense, quantum mechanics is incomplete. Immediately there was a negative reaction from Copenhagen, from Niels Bohr and from Heisenberg and others who said, no, quantum mechanics is complete. This is completeness. Now it seems to me, reading these, really all of them extremely brilliant people, arguing over whether it's complete or it's incomplete, seems like kids in a sandbox, so to speak. Mine is complete, yours is not complete, and so forth. And it got off to what I regard as a very bad start for the attempts to understand what's going on in physics, what's going on in quantum physics. Today we have approximately 24, I've listed around 20 plus interpretations of quantum mechanics in which we try to understand what's going on. And they are in amazing disagreement from one another. Some claim that there is the wave function, which is here, collapses when a particle arrives at a certain point. And others claim, no, there are no collapses. Others go farther and say, there are really no particles. There's just the waves. Followers of Schrödinger, who had hoped to explain everything in quantum physics by his wave theory of quantum mechanics. And Heisenberg, of course, really preferred a particle theory in which, though he felt he had the need perhaps to explain a little bit of the particle as a wave packet, which turned out to be a failure. In any case, the interpretations of quantum mechanics that we have are all over the lot in some respects, and I would argue that it's not possible for all of them to be true because they differ from one another. And it may be that none of them are really correct because they are so different. And I'm hoping that as we go forward in the future, we'll have a little bit more agreement and a little bit different possible ways of interpreting what's going on. This diagram is meant to give people a possibility of thinking that there are paths, even though we can't know them. So let's see, have I exhausted my attempt to describe this problem? I think I may, but we've got a good 10 minutes to go in this lecture. And so perhaps I would like you to realize that you can go to, here on the bottom of this page, the Einstein page, and work your way through it. There's a great deal there, but it's the material that I'm turning into my book. Let's go back to the Einstein page for a moment and see that I've added that same animation on this page. Remember, when you see this work, it's just a simple animated GIF. And if any of you want to write a paper about this or try to explain it to other people, you can come to my page and look at it here, or you can actually copy it. Everything on my website is available in what's called a Creative Commons license. You can take it, show it to your friends, argue over it, and if you can improve it in some way, send me a note telling me what you think about it. So following that new animation, which I just put up today, and I think I need to have it here so you see what I'm doing with it. This is the new animation up today. I have a summary area on Einstein's thoughts about quantum mechanics, trying to get his words to tell us what he thinks is going on, interpreted by me here. And I think that may be the end of the page. No, here's an animation, but it doesn't look like it's working. I need to work on that. And what I'd like to do here, I listed Einstein's objections to quantum mechanics, in summary, the particular words he said. So what I'd like to do now is go to my website. Let's go here on this page, and I'll show you what I'm doing. I'm on my page that lists all the lectures at the moment, and I want to just scroll up until we find Einstein. No, I want to go to my menus here, and you see there's a link to a story about the information philosopher, a blog, which we were using a moment ago, and then books. I just wanted to go here and show how easy it is for you to get my free will book, or my great problems book, or my metaphysics book, and finally the draft chapters of Einstein's My God, He Plays Dice. And I'm hoping that some of you will be interested in working through this page, this draft pages of the book, so as to get a jump on me. And of course, when the book comes out, it will still be chapters that are available here as PDFs. So I have a long background of the chance in physics, and then matter, and then light. So Einstein follows the work of Ludwig Boltzmann in his work on the statistical mechanics of material particles. Very few people know that Einstein, let's see if I've got that in the right place, and I don't, so I need to have this one up. Few people know that Einstein, before 1905 in the great paper on relativity, the three of them, relativity paper, the Brownian motion paper, and the light quantum hypothesis paper, before that Einstein spent 3 years reproducing the results of statistical mechanics, including the Boltzmann formulation of entropy as the disorder based on calculating the number of possibilities there exist for the current distribution of particles in a little box with particles in it, very simple chemical universe they used to call it. And if the particles are all located in one narrow area, the entropy is very low, and left to itself, those particles will rattle their way around and fill up the whole space, and when they're in some random distribution, that's the maximum entropy. Einstein did all of that, just like Boltzmann did, and Willard Gibbs, the American, who did similar work. Einstein did most of it all on his own. He'd read a great deal of Boltzmann, but not all, and he had not read Willard Gibbs, who's the great American founder of statistical mechanics, gave it its name. So in 1905, when he wrote the paper on the Brownian motion, in that work, Einstein disproved that atoms exist. I want to give him credit for saying that photons exist, what he called light quanta, but I also want to remind everybody in this chapter that he also was the one who proved that material particles are particles. Before that, many physicists thought somehow matter was continuous, and we didn't really know the details of it. Chemists for 100 years had known that particles were coming in integer lumps when they combine to form molecules, like one sodium and one chlorine makes sodium chloride, and two hydrogens and one oxygen makes water, H2O. That was known by the chemists, but it was Einstein who actually proved that material particles are there bumping into the pollen seeds in the liquid and making them jump around in what Robert Brown had discovered, and it's called Brownian motion. So there's a long chapter here on Einstein's discovery or hypothesis there are light quanta, and then I repeat his work on statistical mechanics after that. Even though he worked out the theory of statistical mechanics before his great papers, here in 1906, 1907, he found that there is a quantum behavior in statistical mechanics, and there has to be an energy, kind of energy levels, which will turn out several years later, 7 years later, to explain the Bohr atom. And rarely does anyone give Einstein for being the first to see this quantum nature of matter. So right here, I guess I've explained light in general, and here in chapter 6, I present his light quantum hypothesis, and then his Brownian motion, where he proves that the atoms exist. And here the specific heat theory is where he describes the energy levels with jumps between them, a word that's normally associated with Niels Bohr, but Einstein discovered it here in 1907. Then here's Einstein's 1909 work on wave-particle duality. So I've given you a lecture on wave-particle duality, but it barely scratches the surface compared to going and reading as much as I've tried to present in this chapter. Then we make our way up to the Bohr atom, 1913, and now there are energy levels for one electron inside a well, the potential well of the proton nucleus of a hydrogen. And what Bohr did, and it gets refined and refined by others up to Schrödinger, basically we need to solve for the probability waves that can fit into a potential well. And we find that the lowest possible wave has got one node in it, just like a violin string that's vibrating at its resonant, its lowest possible frequency. And then if you go up a little, the energy level has a node in it. That is to say, it comes up, goes through the middle, and comes up the other side, and that's the first excited state. And what you're seeing right there is, just like the probability waves in the space of the two-slit experiment, we solved Schrodinger's equation in that potential function, and we get the energy levels of the hydrogen atom. That's basically the core proof that waves and their equations are solved. They give us probabilities which correspond to the places that electrons can be located in a hydrogen atom or any other atom and so forth, although they're only easy to calculate for hydrogen-like atoms with one electron, or at least one electron in the outer shell. So I'm just working my way through my book on Einstein, and my goal here is to find the time to get back to writing some more chapters. I've written one on the transition probabilities that Einstein was first to calculate on why or how, what is the probability of an electron dropping from, say, level 4 to level 2, or 4 to 3, or 4 all the way down to the bottom one. Here's a story of irreversibility. Here's his Nobel Prize. Here's de Broglie, who came along and was a student of Einstein's work, loved his work, and argued for waves much like the ones that Einstein had told us in 1909. There's very little new that's in de Broglie because Einstein had already described waves for light particles, and what de Broglie did was say, well, maybe electrons, which are material particles, could have a wave-like nature, and he went ahead to do that, and he gave all the credit to Einstein. So I've got a couple more chapters here. Hard to describe what Einstein's about to do in 2425. It's truly amazing. He's done statistical mechanics before, but now he does statistics of different kinds of particles, those that have half integer spin and those that have integer spin, it will turn out to be, and they're called fermions and bosons. They should be called Einsteins or something, because he discovered them. And here I am. I think this is as far as I am at the moment. I'm up to a chapter on the work of Niels Bohr, which was his last attempt to disprove Einstein's photons theory. Really a tragic moment in history. And now I jump ahead. So that's where I am today, and I think I'll probably start to sign off from you today, and encourage you, please take a look at my draft of the book, My God, He Plays Dice, which is right here. Let's zoom in on it a bit, because this is what I would like to be doing in the next few weeks, alongside giving you these 5 lectures every day as well. So let me come back out here maybe. Say thank you very much for being with me today. What we've done is to make the case for probabilities, let's bring that up on the screen behind me, as something which, let's see, I'm in here, and I'll just do this and this and this, and that fits it on the screen a little bit better. Let me come around to this screen, and I'm hoping to draw a parallel between Einstein's gravitation theory, where he has shown that the material distribution in the universe of gravitating matter curves the space. And my parallel is very simple. I'm hoping to have something that's easily memorable. I want to say that the probabilities, and let's bring them up on screen here, that the probabilities of particles arriving into that interference picture you have right there, those probabilities are determined by the boundary conditions of the matter in the sense of the screen, the wall up front with the two slits in it. And those probabilities then are a property of the space. And that's basically my case. Let's see if I can bring this back and this one back. The probabilities are a property of the space. Thank you very much for being with me today. Wow. Okay, let's shut this down, Bob. Stop all. And